Hey, this is Mr. Ariel. I'm here today with a lesson on scientific notation and sig figs. Now, this says part 1, but part 2 is just on the back of your worksheet, and so this one video is going to go over both parts. Let's go ahead and start on scientific notation. That's the idea that any number can be written in the form a times 10 raised to the power of b. So a number like 1,223 can simply be written as 1.223 times 10 to the power of 3. Now, this place where the decimal got put right here, that's very important in scientific notation that a is always going to be greater than or equal to 1, but it has to be less than 10. So if we were to write this and move the decimal, say, 4 places, that would end up being 0.12, but that's less than 1. And then this is the correct form, but if we only move the decimal 2 spots and got 12.23, well, that's greater than 10, and so that is also incorrect. Next up, for these practice problems, we're going to convert the numbers into or out of scientific notation. Now, this number right here is written in standard form, so we're just going to go into scientific notation. And the way I personally do this is I imagine or draw the decimal to be right there, and then I'm going to move it 1, 2, and 3 spaces to end up with 9.224. And we follow that up with times 10, and we have to raise it to the power of 3. And I find a lot of students get confused over whether this is 10 to the positive 3 or 10 raised to the negative 3. And until you get familiar with it, it's probably easiest to memorize things like 10 to the power of 3 is equal to 1,000. And so if we're multiplying 9.224 times 1,000, that's going to get us back to the original answer, and that's correct. If we did it incorrectly and said it was 10 to the negative 3, well, that's the same thing as saying 0.001. I mean, it's 1,000th. So if you were to multiply 9.224 times 0.001, you are not going to get an answer that is 9,224. It doesn't take a lot of practice before you figure out which sign the exponent is going to have. Now I'm going to do this one other problem, and I'm going to ask you to do these 4 on your own. So let's work this problem out. 1.51 times 10 to the 4th. Well, using the trick we just did, 10 to the 4th, that would have to be 10,000. And so that means I'm going to move the decimal 4 places. And what we're really doing is multiplying 1.51 times 10,000. And so if you're wondering, do I move the decimal to the left or do I move it to the right? Well, this would be a really big product we would get right here. And so we know we have to move that decimal to the right. And so I go ahead and write out 1.51, and then I start moving that decimal 1, 2, and I'm going to need some more digits. And that's 3, and that's 4 spaces right there. And so the correct answer to this problem is 15,100. Now at this point, I want you to pause the video and try these 4 on your own. So if you got all those correct, let's go ahead and move on to the next part. Now for significant digits, on the title of the worksheet, it says sig figs, and that's for significant figures. Significant figures is a lot to say every time, so sig figs is how it kind of gets abbreviated. Now, before we get into the rules here on the worksheet, I want you to know that significant figures are used for 2 different things. First, they protect precision that was paid for. Like, for example, in lab this year, you're going to use a scale that can read grams to the thousandths place, like 1.456 grams. That scale costs hundreds of dollars. I mean, it's not like $1,000, but it's not a cheap $20 scale either. Now, imagine that you use this number in a formula, and the calculator gave you a result that's correct math of all of these digits. I like to call it calculator vomit because not all of these digits mean anything. And if you were to stop and round off to this answer and say that it was 1.2, then you are throwing away precision that was paid for. I mean, that scale cost a couple $100, but a cheap $20 scale might have been able to get you to this answer, but the real answer that's still precise might have included a few more decimal places, like maybe it was 1.203 when you finally rounded off. Now, the other thing it does is it avoids invented precision. And so let me set you up with an example over here. If we took a 1 meter rod and we broke it up into 3 equal pieces, A calculator would tell you that that's 0.3333, and I know it repeats on forever. But back to this original measurement, 1 meter, if you only measure it to 1 meter, I mean not like 1.00 meters, the device that you would have used that only measured it to 1 meter would be pretty cheap because it's low precision. It's pretty easy to manufacture, doesn't require a lot of technology to print teeny tiny lines onto it, and so it's a pretty cheap device. Well, in that case, with this low precision measurement right here, when you divide it into 3 equal size pieces, you can only be confident of saying that those pieces are 0.3 meters each. All these other digits that the calculator would tell you are garbage because you're not sure of any more precision than this one measurement right here that had one significant digit. Now, how did I know to round off right here? That comes from the rules down here and what we'll learn to do with math in just a couple of minutes. Now, if you're scratching your head and wondering, well, if we take those 3 pieces that Mr. Ariel says are 0.3 meters and we multiply that by 3 and we get back to the original length of the rod was 0.9 meters, and you're wondering, where did that extra 0.1 go? Well, it didn't go anywhere because, again, we were unsure of exactly how long is this. That original measurement of 1 meter, it's better thought of as being sort of around 1 meter. I mean, close to a meter, but we're not even sure it's an exact meter. And so there is no missing 0.1 meters. And so now let me finish this example up. If we used a measuring device that could give us this measurement, it would have lots of extremely tiny lines on the measuring device for you to be able to read. But if we took that measurement here, and we were confident that the piece was 1.00 meters, that has 4 significant figures. If we divided that into 3 equal size pieces, well, now we could say that each piece is actually 0.3333 meters in length. And if you multiply that by 3 to get back to the original length, you can see that we're a lot closer to the original length that we thought it was of 1.00 meters. And now if you're still scratching your head and wondering about that missing 0.00001 meter piece, remember that back up here with that measurement, we were only sure of this level of precision, and that got us a lot more precision on our answer for each piece, and that's reflected down here where we only have a tiny little bit that doesn't line up if we were to multiply back together to find the original. All right, so that's enough of what significant figures are used for. Let's learn the rules of how to use them. The first rule is that all non-zero digits are significant. So 1,387, well, it's got 4 significant digits. They all count. Next up, zeros between 2 non-zero digits are always significant. So this 0 right here counts as being significant, and so this number has 5 significant digits. Next up is leading zeros are not significant. And so all 3 of these zeros right here are leading because they come before the single value that has 1 significant digit. And the final rule is trailing zeros after a decimal are always significant. So that's these 3 right here. And so this number right here has 4 total significant digits. Now I realize I cut off part of the problem, so let me fix the board real quick. Now for this practice, we're just going to count the number of significant digits. So I'm going to do a couple of these and then ask you to try the rest yourself. So this 0.009, well, the 9 counts because it's a non-zero digit. But both of these are leading zeros, and so this number right here has 1 significant digit. I'm going to try this one right here just to get scientific notation in there. I hadn't mentioned that yet. Both of these digits, 8 and the 1, they're non-zero, so they count. So this number has 2 significant digits. Now, something to memorize at this point is that scientific notation, these numbers right here, never factor into significant digits. And so you can always ignore them when you're counting up significant digits. Now, at this point, I want you to pause the video and try these other 4 problems on your own. So this problem right here, that's 4,015. And so these 3 are non-zero, so they count. And this one in the middle, the 0, is between non-zero digits, and so this one has 4. This one over here has 4, has a 0 between 2 non-zero digits, so it counts, so that all those count. And this one right here is a trailing 0, so that is 5 significant digits. Over here, we can ignore scientific notation. And so this is a trailing 0 after a decimal. It counts. And so does the 1. So that's 2 sig figs. And then over here, now this one's kind of tricky. The 3 counts for sure. And you might think these are trailing zeros, but the rule says trailing zeros after a decimal are significant. And so none of these digits right here count as significant digits. So that's going to be 1 sig fig. Now, if you're kind of wondering about that one, if you wrote 3,000 and you put a decimal place after it, that would be 4 significant digits. I'll abbreviate that 4SF. And the difference is this. Let me describe to you perhaps a Friday night football game where you had to actually go through one of those turnstiles that counts the number of people that have gone through it. I mean, every time you push through the turnstile, it activates a counter that moves a number on a dial. Now, if you went at the end of the night to find out how many people had come to the game through that gate could give you 4 significant figures of precision. I mean, you could tell exactly 3,000 people had come through the gate. No more, no less. But if you didn't have that turnstile and you just simply asked somebody who was standing there, they could give you an answer based on a lot of experience. They could probably tell you, it was roughly 3,000 tonight. And that's this number that has 1 significant digit of precision. You know, it's kind of close to 3,000, but in reality, it might have been 2,750, or maybe it was really 3,250. And you're not really sure where it was exactly. So that's kind of the point of sig figs. A turnstile would have a lot of precision that was paid for, and you'd want to use all that precision in your measurements and calculations. And you'll see a lot of examples of that through the year. So let's move on a little bit. We got to do a couple of practice problems and then we'll be all done. With sig figs, there's some pretty interesting rules that you may not have learned in any class previous to this one. When you do addition and subtraction, you're going to round the answer to the same decimal place as the least precise input. So looking at these numbers right here, this number has 6 significant figures, and this one has 2. But none of that actually matters. This number, because it goes to the thousandths place, is more precise. And this one that only goes to the tenths place is least precise. So when you add them up on the calculator, the 0.4 here, that's the least precise decimal place. I mean, it's the tenths place. And so this answer gets rounded off to the tenths place as well. Multiplication and division, it works a little different. You round the answer to have the same number of significant digits as the least precise input. So here we need to count the significant digits. And this one has 4, and this one has 2. And so when you multiply them together, the calculator will give you a longer answer, but it gets rounded back to have 2 significant figures. Now, if you end up doing a combination of addition, subtraction, multiplication, and division, kind of like this problem here uses addition and multiplication, well, you just ignore the addition subtraction rule and you use the multiplication and division rule. And so out of this, we've got 3 sig figs here, 3 sig figs here, and 4 there. So the answer gets rounded back to have 3 significant figures. Let's get into some practice problems. Now, if you plug these numbers in on the calculator, you're going to get 103.734, and it goes on for a while. But we're doing division, and so we have to count up the sig figs. This number has 1 significant digit. Remember, we did this on the previous side of the paper. And then that one has 4. And so when we round this answer off, we're going to say that that is 100 because that has 1 significant figure. To be fair, it's a little more clear if you write it like this, 1 times 10 to the second, because it means 100. Now I want to jump over here and do this one. If you plugged them in the calculator or really just did that in your head, it would come out to be 2008. But this is an addition problem, and so we have to round the answer to the least precise decimal place. And so this number right here is to the ones place, and so that's kind of precise. But this number over here, none of these are significant. This is the only significant decimal place. Again, it's like the football game where you say that about 2,000 people came in. This is the only digit you're sure of in this entire number. It's around 2,000. And so for this one, we have to round back to the same place. And so that's going to be that thousandths place. And so this is going to round off to be 2,000. Again, going back to that football game example, if you asked the person at the gate and they said, oh, it's roughly 2,000 tonight. Well, if you stood there and 8 more people walked through the gate right at that moment, would there now be exactly 2,008 people in the stadium? I think you know the answer is there's still about 2,000 people in the stadium. You can't be any more sure than that based on that original 2,000 number. Let me do one more practice problem that's a little more normal than that one, and then I'll turn you loose. We're going to do a division problem right here, and we have to count up sig figs because we're going to have to round off to the same number of sig figs, and all 3 of these are significant, but that one's not, and so that's got 3 sig figs. And this one over here has 5 sig figs. So when you plug them in on the calculator, you're going to get 31.55122, and it goes on for a while. But for division and multiplication, we round back to the same number of significant figures as the least precise number. And so that's going to be 3. So that's 31.6 as a final answer. Now go ahead and pause, try the other 5 problems, and when you come back, I'll have them all worked out on the screen. All right, here are the rest of the problems. I cut out the part of the video where I worked them out because the video is getting too lengthy already. But if the work on the screen doesn't really explain why the answer is the way it is, feel free to ask me about it in class. I am happy to help you learn this material. Now, this is the end of the video, so I hope it's been helpful to you today. And as always, thanks for watching.